Imagine building a language model that beats a 14 billion parameter giant at coding, but it runs with the blazing fast latency of a tiny 2.5 billion parameter model.
Right, which sounds impossible.
It really does. But welcome to AI Paperslop. This is the series where we summarize the latest AI and tech papers for you, the ML engineers and researchers who are out there building on the bleeding edge.
And today we are jumping straight into the Mellum2 technical report. This was published by JetBrains and Constructor University.
Yeah, and let me just give you the absolute bottom line right out of the gate here. Mellum2 is an open-weight, 12 billion parameter mixture of experts language model, and it is custom built specifically for software engineering.
Exactly. And the crazy part is it achieves this massive performance while only using, 2.5 billion active parameters per token?
2.5 billion, yep. So it matches or completely outperforms 7 to 14 billion parameter dense models on the major coding benchmarks.
But its inference speed is effectively identical to a tiny 2.5 billion dense network.
Which is huge.
Right.
They trained it on 10.6 trillion tokens, and they released both an Instruct and a thinking variant. So, if you are deploying models locally or trying to optimize for highly constrained environments like an IDE, this paper is basically a masterclass.
It really is. It's all about squeezing frontier-level performance out of commodity GPUs. And the entire architecture is just this study in extreme latency optimization.
Because building a model for an IDE means you have a hard ceiling on generation speed, right?
Exactly. You are targeting inference on a single H100, or even just a consumer GPU. And every single architectural choice they made, from the attention heads to the pre-training data mix, it was all ruthlessly ablated to serve that specific latency constraint.
They didn't just stumble into a 12 billion parameter MoE.
No, not at all. They actually arrived there after discarding architectures that, honestly, most of the industry currently assumes are just the default.
Right, because initially they tried deep dense models, wide dense models, even that DeepSeek style multi-head latent attention, the MLA stuff.
Yeah, but at a 12 billion parameter scale, MLA required a latent rank that just introduced way too much training complexity and too much overhead.
And standard dense models just couldn't hit the speed to quality ratio you need for instant autocomplete.
Right, you need that to be instant. So that constraint drove them to a 64 expert mixture of experts architecture.
But they're routing to exactly 8 active experts per token.
Yes, and if you've ever experimented with sparse architectures yourself, you know there's a really severe penalty if you push sparsity too high on a smaller model.
Yeah, I think they tested routing to just 2 experts at one point, right?
It did. And sure, it made inference like 1.5 times faster, but the quality degraded unacceptably.
Because a 12 billion parameter model just doesn't have the baseline capacity to survive that level of sparsity.
Exactly. But by activating 8 out of the 64 experts, they found this optimal frontier. The total parameter count is large enough to memorize all the long tail of obscure programming APIs.
But the active compute footprint per token stays firmly locked at 2.5 billion.
Right. And that obsession with the compute footprint carries right over to their grouped query attention setup.
Oh yeah, they landed on 4 KV heads.
Not 8, not 2, just 4.
Which makes sense. I mean, for anyone out there serving concurrent requests, you already know the KV cache is your ultimate bottleneck.
It's a memory bandwidth issue. It's not a compute issue. When a model generates text concurrently for multiple users, the GPU is spending way more time just moving the KV tensors from high bandwidth memory to the compute cores.
Then it spends doing the actual matrix multiplication.
Exactly. So JetBrains tested 8 KV heads, and the memory footprint just totally choked their throughput. They had to drop the batch sizes.
But then when they ablated down to 2 KV heads to try and save memory, the model started losing context resolution.
Right, it started failing coding benchmarks. So 4 KV heads was the sweet spot. It had the memory bandwidth requirements of an 8-head setup, but it perfectly preserved the output quality.
That brings us to the sliding window attention, or SWA, which is where I think this paper gets incredibly clever. Oh, this part is brilliant.
Yeah, they didn't just apply SWA blindly. They used a 3-to-1 pattern. So 3 out of every 4 attention layers are hard constrained to a 1024 token sliding window.
And then only the 4th layer computes full dense attention across the entire context.
Right, because paying the quadratic compute tax of full attention on every single layer is just entirely unnecessary for code generation.
Mostly, attention heads are just looking locally at syntax anyway, like matching a bracket or checking a local variable type.
It's so interesting to think about this in terms of hardware architecture. It's very similar to how a CPU uses an L1 versus an L3 cache,
Oh, that's a great analogy.
or even like a sliding convolution in computer vision. You have these three layers acting like your L1 cache. They only care about the immediate 1,000 tokens of local syntax. They just slide along the text, extracting those localized features.
Right.
And then that fourth full attention layer acts like your L3 cache. It aggregates all those local features and computes the global structural dependencies for the entire file. And that mechanism completely breaks the quadratic scaling barrier for 75% of the transformer block.
It's so efficient.
But honestly, arguably the highest ROI architectural decision wasn't even the attention mechanism. It was the multi-token prediction, the MTP head.
Oh, wow, yes. They added a single parallel transformer module on top of the base model.
Right, to predict the next token, plus one additional future token during pre-training.
And adding that single MTP head boosted their human evil score by an astonishing 10.4 points.
10.4. And it only increased the pre-training compute cost by like 7%.
You just rarely see that kind of asymmetric alpha in model training.
You really don't. And the underlying physics of why MTP works so well for code is fascinating.
How so?
Well, when you force a network to predict token n+2, you are mathematically forcing the hidden states of token n to contain broader semantic planning.
So it can't just memorize surface-level syntax anymore.
Exactly. It can't just look at its immediate neighbor. It has to internalize the deeper algorithmic structure of the code to accurately guess what happens 2 steps into the future.
So it acts as this massive regularizer on the representation space.
Yep.
And for the ML engineers deploying this, the MTP head gives you a huge deployment bonus. That secondary prediction head doubles as a built-in draft model for speculative decoding.
Right, which means you don't need to load a separate, smaller draft model into memory.
Which saves even more bandwidth. The model just drafts its own future tokens natively, giving you a massive speed up during inference.
So JetBrains built this incredibly lean, hyper-optimized engine.
But, you can't just throw 10.6 trillion tokens of raw data at an engine like this and expect it to learn programming.
No, you need a highly structured pre-training curriculum.
Okay.
And they use 3 distinct phases, following a very strict web early, curated, late paradigm.
Okay, break that down for us.
So phase 1 is foundation building. That consumes about 58% of the total compute budget. And this is mostly diverse general web data.
So the goal here is purely structural, teaching it grammar, basic reasoning, language statistics.
Exactly. Then phase 2 triggers the quality uplift. That's about 26% of the run. This is where they aggressively upsample high-quality code, mathematical proofs, algorithmic tutorials.
Right, until that stuff makes up about 42% of the training mix.
Yep. And finally, phase 3 is capability sharpening, the last 16% of the tokens. Here, code becomes 59% of the diet, and they initiate a linear decay of the learning rate down to 0.
Which makes sense. You only expose the model to the absolute highest density, highest difficulty data when the learning rate is dropping.
Because that is when the network is annealing. It's locking in those deep conceptual representations.
Now, looking at the fill in the middle, or at FEM scheduling across these phases, there is a really interesting anomaly here.
Oh, the FEM rates, yeah.
Yeah, because for a model destined for an IDE, FEM is the core mechanism. It allows the model to see code before and after the cursor to autocomplete the middle. In phase 1, they set the FEM rate to 50% to teach the model bidirectional context. But then in phase 2, right when they introduce the most complex math and curated code, they slash the FEM rate down to 10%.
Which seems counterintuitive at first.
It really does. Why would they aggressively suppress the autocomplete training right when the data gets good?
Wait, I guess if you are feeding the model complex mathematical proofs and step-by-step logic in phase 2, FEM would tear that logic apart, right?
Exactly. You would be completely disrupting the causal chain. If you take a rigorous algorithmic tutorial and scramble it into a fill-in-the-middle objective, the model loses the step-by-step reasoning pathway.
Oh, wow.
Yeah, so by dropping FEM to 10% in phase 2, they force the network to process that ultra-high-quality data strictly sequentially, left to right.
So it actually learns how to solve problems sequentially.
Yes. And then once those deep causal pathways are permanently locked into the weights during phase 2, they bump the FEM rate back up to 50% in phase 3.
But strictly for source code, right? Strictly for source code. Just to snap the model back into its IDE completion behavior right before the training run ends.
That is just a brilliant way to balance deep reasoning with product-specific formatting.
It really is.
Let's pivot slightly to the optimization side, because JetBrains abandoned standard AtomW for the distributed Muon optimizer, specifically using the Moonlight configuration.
Right, and Muon is rapidly becoming a critical tool for training large-scale mixture of experts models.
Why is that? What's wrong with AtomW here?
Well, AtomW scales weight updates, using the inverse variance of past gradients. And in highly sparse networks like MoEs, where certain experts might not see tokens for several steps, AtomW can lead to vanishing updates, or even dimensional collapse.
Like certain latent dimensions just die off.
Exactly.
And Muon prevents that through orthogonalization.
Yes, Muon applies orthogonalization-based updates directly to the hidden layers while keeping standard Atom for the embeddings and outputs. By explicitly orthogonalizing the update matrix, Muon guarantees that the update maintains full rank. It forces the network to utilize all available latent dimensions.
Which prevents the representation collapse that typically plagues MoE routers.
Right. JetBrains reported massive stability and loss improvements over AtomW. If you are training sparse architectures, Muon is proving to be incredibly robust at scale.
Speaking of scale, I want to highlight something from the data pipeline side of this pre-training run, because it's honestly the ultimate reality check for anyone building models, the hash sorting bug.
Oh man, the bug.
Yeah.
Every petabyte scale pipeline has ghost in the machine.
Yeah. So during training, they discovered a bug where their hash sorting algorithm was placing exact duplicate chunks of data at the exact same offset across every single data shard.
Right.
Which created these periodic synchronous downward spikes in the training loss across the entire cluster. And fixing a live distributed data pipeline at this scale is just a logistical nightmare.
A total nightmare.
So because they verified it wasn't destroying the MoE router's auxiliary load balancing loss, they just left it running.
They did. Look, engineering at this scale is an exercise in pragmatism. Cluster compute time is incredibly expensive.
Right.
If a pipeline bug is just creating a periodic artifact that doesn't destabilize the gradients or cause router collapse, you don't halt a massive H100 cluster to rebuild your petabyte data shards.
You just monitor the auxiliary loss, ensure the experts aren't completely unbalancing, and you let the run finish.
Exactly. You just push through.
Okay, so the model finishes pre-training on 10.6 trillion tokens, but it only has an 8,000 token context window, which, if you are integrating this into a modern IDE, 8K is nothing.
No, it's tiny. The model needs to ingest entire repositories.
Right, so they needed to extend this to a 131,000 token window. And they did it using layer selective yarn.
Yeah. Yarn, which is yet another rope extension, modifies the wavelength of the rotary position embeddings. It interpolates to longer contexts rather than forcing the model to extrapolate into unseen positional space.
But applying yarn uniformly across the entire network would have been a mistake here, right?
Exactly. Because of the 3-to-1 sliding window attention architecture we talked about earlier.
Oh, right. Because those sliding window layers are hard-coded to only ever attend to a 1,024 token span.
Right. So scaling their positional frequencies to accommodate 131,000 tokens is mathematically useless. And worse, it unnecessarily perturbs weights that are already perfectly optimized for short-range syntactic dependencies.
Oh, I see. It's like putting reading glasses on the full attention layers so they can see further, but leaving the sliding window layers alone because they only ever look at what's right in front of their face anyway.
That is exactly what it's like. By applying yarn only to the global full attention layers, they preserve the local feature extraction while teaching the global layers to see across the entire repository.
It's an incredibly elegant ablation.
It really is.
And to make sure the model actually understood how to use that massive context, they implemented repository-level FEMM during this extension phase.
Right. Instead of just showing the model random files, they programmatically packed related files from the exact same repository before the target file.
Which mirrors a developer's actual workflow perfectly. I mean, if you are writing a function in main.py, you're relying on an interface defined in utils.py.
Exactly. So by packing utils.py into the context window before applying the fill-in-the-middle objective on main.py, the model natively learns cross-file dependencies.
It learns to actually search the extended context for type definitions and class structures, rather than just hallucinating them.
Yep. So at this point, we have a highly optimized base model. It can read a 131K context repo and generate code efficiently.
But a base model isn't an assistant. It needs alignment to follow instructions.
Right, which brings us to the post-training pipeline. JetBrains split the model into an Instruct variant and a thinking variant. They use supervised fine-tuning, followed by reinforcement learning with verifiable rewards, or RLVR.
Now, the SFT phase had one particularly amusing hurdle, the identity crisis.
Oh, that was funny.
Yeah, because they heavily utilize synthetic data for fine-tuning, the model absorbed the artifacts of the models used to generate that data, so Mellum2 kept confidently hallucinating that it was developed by Google.
Even though no Google models were used, it's a ubiquitous problem in the synthetic data era. The engineers had to aggressively oversample self-identification dialogues just to force the network to internalize that it is Mellum2, created by JetBrains.
That's hilarious. But the core driver of the model's performance is really that RLVR pipeline. And notice they completely bypass standard RLHF reinforcement learning from human feedback.
Right. Because human preference models are incredibly noisy, and human graders are expensive and slow. But more importantly, software engineering and mathematics are deterministic domains.
You don't need a human vibe check to tell you if a sorting algorithm works.
Exactly. You use an execution sandbox, you use symbolic math verifiers. The reward signal is absolute, binary, and verifiable.
The code either compiles and passes the hidden unit tests, or it throws an error.
Yep. And this allows for massive automated reinforcement learning without the bottleneck of human preference models.
But running asynchronous RL on a mixture of experts model in BF16 precision introduced a really deep systemic bug that they had to solve with something called ice pop truncation.
Oh, this is deep in the trenches of ML engineering, but it's critical to understand if you're doing RL on sparse models.
Right. So what's happening here?
Well, it's a fascinating numerical edge case. In an asynchronous PPO setup, you have separate inference engines running the rollouts to generate code, while a training engine calculates the loss and updates the weights.
Okay, so two separate engines.
Right. Both machines are using the exact same weights at any given microsecond. However, because of how BF16 floating point math rounds values across different GPU hardware topologies, the MoE router might calculate a slightly different probability distribution for a token on the inference machine versus the training machine.
Meaning the inference rollout sends a specific token to, say, expert 3, but during the forward pass on the training engine, the router calculates that it actually should have gone to expert 5.
Exactly. And when those routing distributions mismatch, the probability ratio used in the PPO loss calculation diverges wildly.
Oh, that sounds bad.
It is. Standard PPO uses clipping to handle probability divergence, but clipping assumes the underlying token representation is still valid. In MoE, if the token was routed to the wrong expert, its entire hidden state representation is corrupted.
Wow. So if you let that feed into your gradient, a tiny handful of drifted tokens will just completely explode your training run.
Completely exploded. So instead of clipping, they implemented ice pop. They look at the probability ratio, and if it exceeds a threshold due to this hardware rounding drift, ice pop safely truncates, meaning it completely drops that token from the loss calculation.
It just throws it away so it doesn't corrupt the weight update.
Yep. It is a mandatory stability fix for asynchronous RL on sparse architectures. But, while ice pop solved the hardware level routing, they also had to solve a behavioral issue during RL, the concision problem.
Yes. This is where things get slightly philosophical. So they are training an Instruct model, which is supposed to give fast, direct answers, and a thinking model, which is allowed to generate long internal reasoning traces before outputting code.
Right, and during the early RL runs, the Instruct model naturally started generating internal thoughts.
Like it would output phrases like, wait, let me check this calculation, or actually, let me think about the edge cases, right in the middle of its standard response.
Exactly.
Okay.
His reasoning works. The RL algorithm discovers that if the model generates more tokens to map out the problem, it has a mathematically higher chance of passing the unit tests and getting a high reward from the sandbox verifier.
So emergent reasoning is literally the optimal strategy for the model.
Yes. But JetBrains instituted a massive penalty for reflection trigger words like wait or actually in the Instruct model. They effectively slapped the model's wrist every time it tried to think out loud.
They forced the Instruct model to be purely concise. All of that rich internal reasoning capability was stripped out and reserved exclusively for the thinking variant.
They did.
I have to push back on this engineering choice, honestly. We are witnessing an intelligence natively discovering that an internal monologue improves its accuracy, and we are heavily penalizing the word wait. Are we artificially lobotomizing the model's emergent reasoning just to force it into an arbitrary product category? We are literally punishing the network for thinking.
I mean, if you view that model purely as a cognitive research subject, yes, it feels like a lobotomy. But if you view it as an enterprise product, it is a non-negotiable feature.
Really, non-negotiable.
Totally. If you were typing in VS Code and you hit Tab for an autocomplete, you cannot afford to wait 4 seconds while the model generates a paragraph of internal monologue about variable scoping.
Yeah, that's true.
In the context of an IDE, an internal monologue is literally just latency. It destroys the user experience. So the engineers aren't punishing the network for thinking. They are constraining its generation path to fit the latency budget of a specific tool. If a developer wants to brainstorm complex architecture, they just load the thinking variant.
Fair point. Product requirements dictate the weights. Let's look at the final scorecard for all this optimization, though. How did this 2.5 billion active parameter model actually perform?
Remarkably well. The RL thinking variant absolutely crushes Evol Plus, which is the gold standard for robust function synthesis. It scores 78.4%.
Wow.
That comfortably beats models twice its size, including the 14 billion parameter Minstrel 3. It also unlocks high-level algorithmic reasoning on LiveCode Bench, operating right at the level of top-tier dense models.
But it does have a deliberate blind spot.
It does. It significantly lags on GPQA, which tests graduate-level science trivia and general knowledge benchmarks like MMLU Redux. But this is an unapologetic trade-off.
Right. They deliberately sacrificed broad encyclopedic world knowledge to maximize the parameter budget for elite software engineering.
Exactly.
Which leaves you, the AI developer or ML engineer listening to this, with a massive shift in perspective to chew on. I mean, Mellum2 proves that with ruthless architectural ablation, clever MoE sparsity, and verifiable reinforcement learning, a model using only 2.5 billion active parameters can outperform a 14 billion parameter model at complex coding tasks.
It really changes the math on deployment.
It does. So as the industry begins hitting the physical memory walls and economic limits of massive, dense models, is this the trajectory we are on? Are we moving away from the dream of deploying a single godlike generalist model locally and instead heading toward a future where our hardware natively runs a fragmented swarm of highly specialized, hyper-optimized MoE agents, each surgically constrained to perfectly execute one specific task?
I think the evidence here is clear. When your compute and latency budgets are fixed, extreme specialization beats generalization every single time.
Something to keep in mind for your next training run.
Well, that is a wrap for this discussion on AI paper slop. Take these latency constraints, dig into Muon orthogonalization, explore verifiable rewards in your own deterministic pipelines, and we will catch you next time.